Next section of the textbook is called Effect on Temperature of Solubility. So we're going to look both at the solubility of gases and solids in liquids on this one. So it doesn't matter what the gases always become less soluble in water at high temperatures. This plays a part because of the fact this is why you can't necessarily have the same fish in the south as you do in the north. The north has fish like pike in it, but you don't have pike down here. And that's because of the fact that fish need dissolved oxygen in order to survive. The average temperature of lakes up north are much colder, so they have much more oxygen. You take that same pike and put it into a warmer water here in the south, and there's less oxygen, it will actually die from lack of oxygen. So it doesn't matter which kind of gas it is, it's going to become less soluble at high temperatures. So your sodas are always going to have less going to fizz more when you open them if they're at room temperature than they are if they have been in the refrigerator, because more carbon dioxide comes out at room temperature. Ionic compounds, most become soluble at high temperatures, but not all. This figure over here shows, I did say the other day that sodium chloride has very little effect in the temperature as a factor, or solubility as a factor of temperature. And so you can see here there's a slight increase, but it's not very much at all. And so we looked at it at 24 degrees and it was 34 grams. It gets to about 40 grams per 100 milliliters once I get to boiling point. Okay. But most of these you see they increase the solubility with temperature. Sodium nitrate definitely does, calcium chloride, lead 2 nitrate, potassium nitrate, KCl, potassium dichromate, potassium chlorate. However, there is one on here, cerium 3 sulfate, that actually decreases solubility at the room temperature range here, and then levels out as you get warmer there. So not all increase solubility with increasing temperature, but most do. This is just an example of one that does not. So how do you predict whether something is going to increase its solubility by increasing the temperature? Basically, if you do so, and this is the same figure from the previous slide, if the solution becomes hot when you're dissolving it, then to warm the solution is going to decrease the solubility. If the solution becomes cold when you dissolve it, then it's going to increase the solubility when you warm it. So if it becomes cold and I add more heat to it, that is going to allow it to dissolve more. But if it's hot and I add more heat to it, it's going to decrease the solubility. And this is a factor of Le Chatelier's principle. Le Chatelier's principle is something you're going to see in this chapter and several chapters. Basically, it talks about an equilibrium, which solubility is disturbed by a change of temperature, pressure, concentration. Then the system shifts in such a way to counteract that. The human body is a great example of Le Chatelier's principle. The human body, if you're cold, you do what? You shiver. Why? The muscle movement generates heat. If you're hot, you sweat, because the evaporation of the water off your skin cools you down. If you come up the steps, your heart rate increases because you need more your heart rate increases, but so does your respiratory rate because you need more oxygen to go to those muscles. As soon as whatever those changes have go back, then you stop doing those things. So those are all examples of Le Chatelier's principle. Now we're going to look at the effect of the pressure on solubility for gases. We're only talking about gases here. Adding pressure to a solid into a liquid doesn't do anything. But if I increase the concentration or the pressure of a gas above a liquid, more will dissolve. Okay? And that tendency is called Henry's law. So the solubility of a gas is directly proportional to the partial pressure of the gas above the solution. And this is the formula that's given to you at the end of the chapter and therefore on the formula sheet. So S stands for solubility. And it's usually in grams per 100 milliliters, but doesn't have to be. So this is solubility. It's in some concentration, grams per 100 milliliters. The problem we're getting ready to do is in moles per 100 milliliters. So some type of concentration unit. This is a constant that is gas specific. So it's not like, when I say constant, it's not like the 8.31, which is constant no matter what the problem is. This is gas specific. And this is the partial pressure. And it doesn't matter what the units are. It can be in millimeters of mercury, atmospheres. It doesn't really matter. Those are the two big ones that we use. Okay. So this is showing two different solutions here. I have, this is another unit of pressure here, bar. Okay. I have 1 bar, and so I basically have 1, 2, 3, 4, 5, 6, 7 molecules of gas, and then 10 total, and 3 have gone into solution. So I have 10 molecules of gas, and at the pressure of 1 bar, I have 3 have gone in. If I increase this to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. If I double this, because I doubled the pressure, then I have doubled from 3 to 6 the number of gaseous molecules that have gone here. So by increasing the number of molecules above, which is the partial pressure, I increase the solubility there. Okay? So let's do a problem. And there's 2 ways to do this problem, so I'm going to pick 2 different colors here. Okay? So the solubility at 25 degrees, so we're going to start the same way. We're going to start writing out our information. I have a pressure of 1 atm, which is atmospheric pressure. And I have a solubility of 6.8 times 10 to the minus 4th. Like this one's actually moles per liter. I said it was moles per 100 milliliters, but it's moles per liter. It wants to know what is the solubility when the partial pressure is 0.778. That's atmospheres. Okay, so if I want to use that formula that's given as is, its solubility is equal to KH times P. They don't, KH is not something you're going to know or can look up on the periodic table. So I'm going to first solve it with what I know to find KH. So my solubility that I know is 6.8 times 10 to the minus 4th. KH is what I don't know. And my pressure was 1.0 atmospheres. So that means that my KH is 6.8 times 10 to the minus 4th. Don't worry about the units for it. Okay. And now I'm going to use this KH to find the solubility that I don't know. So again, same formula. Solubility is now 6.8 times 10 to the minus 4th. But now I'm going to use my new pressure of 0.78, and I get 5.34, 5.30 I should say, times 10 to the minus 3, and that is moles per liter. So the solubility, whatever the solubility unit of the one given, it's the same here. Okay. All right. But there's another way that I can do this. Okay, so I'm going to show you 2 ways. You choose which way makes more sense. This is using the formula that's given to you on the formula sheet. But the other thing is that for a given gas and a given temperature, this K is constant. So if this K is constant, I can basically say that S divided by P is equal to KH, which is basically what I did here. And so therefore, S1 divided by P1 is going to equal S2 divided by P2. Okay? So basically, I just solved them 2 different things. So I'm going to make this one 1 and this one 2. It doesn't matter which one's which, it's just they're together. So S1 was 6.8 times 10 to the minus 4th over 1 atmosphere is S2, which I don't know, over 0.78. So I need to cross multiply, so I have 6.8 times 10 to the minus 4th times 0.78 is equal to S2 times 1. So I need to divide both sides by 1, so 6.8 times 10 to the minus 4th times 0.78 divided by 1 is equal to S2. And so S2 is still going to be equal to that 5.30 times 10 to the minus 3 moles per liter. So there's two different ways of doing this problem. You can choose which way you want to do. It does not matter. And that's the end of this video.